Okay, so today we're going to be talking about groups. Now, groups are a very important mathematical object, and we deal with them in all different branches of mathematics. So let's define what a group is. So a group is a set of symbols and an operation. We normally call that operation multiplication, but in special cases we call it addition. So we call a group with this operation, we call it G comma star. We put that in parentheses just like an ordered pair. And G is going to denote the set of symbols, and star is going to denote the operation that we're putting on the group. Okay. And groups have the following properties. So the first property that a group has, that all groups have, is closure. So what does closure mean? Formally, it means that if we take any two elements, say A and B in our group, A star B is also in our group, which means that it's closed under the operation. Secondly, we have associativity. Now, associativity means that we can move around the parentheses. So that means if we have A, B, and C, any A, B, and C you want in the group, and we have A star, and then in parentheses B star C, that's the exact same as in parentheses A star B star C. Our next property is that we have an identity element. And this identity element is unique. In group theory, we call it E most of the time. Sometimes we'll call it 1, but that's mostly reserved for rings and fields. And this property that E has is that for any element G, including E itself, if we take A times E or E times A, we're going to get A back. Now, our last property that makes something a group is an inverse. So that says for any A in G, any element you want in G, there exists a unique element A inverse, such that A inverse is the same as A inverse A is E, and that E is our identity element. Okay, so now that we actually have the properties of a group, we also have a bonus property of a group, and that property is called commutivity. And what commutivity says is it doesn't matter what order we multiply things in. So we can take any A and B, and A times B is the same as B times A. And if a group has this property of commutivity, then we call that group abelian. Okay, so let's look at our first example. So for our first example, we're going to look at something we all know. We're going to look at the integers with addition. So remember what this means. It means that our group is the integers and our group operation is addition. So first, let's show that it's closed. Well, we know from elementary school that if I take two integers and I add them together, I get another integer. It might be positive, it might be negative, but it's still going to be an integer. Secondly, we're going to look at associativity. This is another property that we're all familiar with integers at the very least. So it doesn't matter what order we add integers in, we're still going to get an integer out. And we're going to get the same one no matter how we order our addition. Next, we're going to look at the identity. So we claim that 0 is the identity element, and we all know that it's true because if I take 0 and I add it to any number, I'm going to get that number back. And it doesn't matter which order I add 0 to it. So, for example, 3 plus 0 is the same as 0 plus 3, and that's 3. And finally, to show that it's a group, we're going to look at our inverse elements. So we claim that if I have any integer a, that its additive inverse is going to be negative a. Right? So if we look at, for instance, a plus negative a, we know that's the same as a minus a. And anything subtracted from itself is going to give us 0. Next, we look at negative a plus a. Well, if I take negative 3 and I add 3 to it, for instance, I'm going to get 0 out. So this satisfies everything we need for a group. Now, this group is also abelian. So that's just because if I take 2 plus 5, that's the exact same as 5 plus 2. Right? It's going to be 8 no matter which way we add things. So now let's look at a second example. For this, we're going to look at the roots of unity. So that's all complex numbers such that raising it to the nth power, where n is a fixed number, a fixed positive integer, is equal to 1. And we're going to look at our group operation of multiplication. So the first thing we have to note is that if we have any complex number in our set, we can write that as z to some power k. For any integer k. Well, for some integer k. It couldn't be any integer k because then it would be going around the circle. So let's look at closure first. So if I have z to the k and z to the l, what I want to do is I want to show that z to the k times z to the l, all raised to the nth power, is going to give me 1. Because then it satisfies the property of being in the set U. So in order to do this, we're just going to take z to the k, z to the l, raise it to the nth power, and argue that we get 1 out of it. So that's the same thing as z to the k plus l to the nth power. And since an exponent to an exponent is multiplication, we can just flip them, and we get z to the n to the k plus l, which by our property of u is 1 to the k plus l, which is 1. So it satisfies being in the set U. Next, we're going to look at associativity. So we're going to say z to the a times the quantity of z to the b, z to the c is z to the a, z to the b times z to the c. So in order to do that, we multiply z to the b, z to the c, and we get z to the b plus c. Now we're going to take that, and we're going to multiply it by z to the a. And we get z to the a plus the quantity of z to the b plus c. And since we're dealing with integers in the exponent, we can just shift those parentheses over, and we get z to the a plus b plus c. And now we split that out again. We get z to the a plus b, z to the c. And we split that down again, and we get z to the a, z to the b, times z to the c. So that satisfies our associativity. For our identity, we're going to claim that z to the 0, which is 1, is our identity element. So what we're going to do is we're going to take an arbitrary z to the a in our set U. And when we multiply that by z to the 0, we're going to see that we get z to the a plus 0. And as we know with our properties of integers, that anything plus 0 is itself. So we get z to the a. Now if we multiply it the other way, z to the 0, z to the a, we get z to the 0 plus a. And as we know again, 0 plus a is a. So our identity actually works. Finally, we have to show that it has inverses. So we claim that if we're given a z to the a in the set U, what we're going to do is claim that z to the negative a is actually z to the a inverse. Okay, so we're just going to do the calculations here. So z to the a, z to the negative a, that's z to the a plus negative a. And as we saw in our example, that's 0. So we have z to the 0. Multiplying it the other way, we have z to the negative a plus a, and that's also z to the 0. So our inverse is what we claim it to be. And therefore U, with multiplication, is in fact a group. Now we also have a bonus with this group too. We have that it's abelian. And to show that, we're just going to take two arbitrary elements of our set U, z to the a, z to the b, multiply them together. We get z to the a plus b. A and b are integers, so we can flip them because the integers are commutative. And we get z to the b plus a, and that gives us z to the b, z to the a. So in total, U is an abelian group. And just as a note, we use the properties of integers a lot in this. And it's actually no surprise that when we talk about this, we are actually saying that the nth roots of unity, which is what this set is actually the exact same thing as the integers modulo n. Finally, we're going to look at a non-example. And for this example, we're actually going to take our roots of unity, but instead of looking at the operation of multiplication, we're going to look at the operation of addition. So this isn't a group because it's not even closed under the operation of addition. If we take 1, which is in our set, it's the identity element for the multiplication, and we add it to itself, we get 2. And we're assuming that n wasn't 0, so 2 to the n is never equal to 1 for any n greater than 0. Therefore, it's not closed, so it's not a group.